Yeah, I'll just remind you of what we were doing on the conic sections, and we'll finish them. We may lose class on Monday too. I've already put off the conic sections due date, I think, till Monday. Remember, there are 4 conic sections. One of their important features is that if you take any second degree polynomial in 2 variables, here with a, b, then with not all the coefficients 0, these have solutions that are either conic sections, so it makes sense. It's important to draw. This is supposed to, in some sense, the easiest thing after a line, right? If A, B, and C are 0, you get a line out of this. And then if you have the squared terms, you can get a conic section. If you, for some of these cases with the squared terms, or if they all drop out, you can get a degenerate case. Or you get no solution if you put positive number equals 0, for instance. So we said that before. That's one of the importances of this. Another one is that they come up so much in practice, right? There's lots of things we said in nature that follow this. All right, last. Things you put in your backpack and they disappear. Maybe I don't have it. If I were to throw a ball down on the ground and bounce it, and it goes like this, bounce, bounce, bounce. What is this here? What is this bounce shape? Yeah, it's a conic section. Ignoring air friction, it's pretty nearly a parabola. According to Newton's theory of gravity, if you're in a constant gravitational field, like near the Earth, gravity is nearly a constant. Within a constant gravitational field, and ignoring air friction, a ball would execute a perfect parabola. Actually, gravity isn't quite constant, and if you go far enough away, it starts to change. And so actually, if you threw the ball and it could travel through the Earth, it would actually do a nice ellipse with the gravitational field. But the point is, there's lots of real things in real life, like a bouncing ball does that, or we said a lampshade, when you turn the lampshade a little bit. Here's your lampshade, and the bulb here comes out and makes a cone, makes a circle on the ceiling, or if you tilt the lampshade just a little, it makes an ellipse. If you tilt it more, if you look at it intersecting the wall, it makes a hyperbola on the wall, right, because now it's a steep angle. So you get all the conic sections with your lampshades. They use them in flashlights, right? You got a flashlight here, ideal flashlight. The light bounces off the back surface and into a beam, and so you get a circle down at the end that's from the parabolic surface bouncing all the light off the back. Then there's a big circle, because the light coming out of here comes out in a cone, and that's the cone coming out here. So the light circles from light coming out the front, and the bright circle in the middle is from the parabolic thing from your flashlight, and all sorts of those. Your satellite TV dishes are trying to take roughly parallel rays and refocus them to a point. And so all those things come up in lots of neat applications too. So we said one way to define those is by intersecting a cone, but another way, right at the end, we said, can be done in coordinates, something that ancient Greeks didn't have. And the ellipse, the first of the conic sections, there's the ellipse, the circle, the parabola, and the hyperbola. And the ellipse, we're going to say, we wrote this before, but it's the set of all points that such that the sum of the distances to two given points, called the foci, is constant. Let's say it's some constant 2a. A is a number you give me, a positive number, right, since it's supposed to be a distance. Here's what the ellipse is by that definition. I brought these section cups here. This is going to be one focus of the ellipse. Get the board to stay still. And this is the other focus of the ellipse. And this length of the string is 2a, right? It has to be the constant distance. And the idea is the distance from this point to the pin and back to the other point is always constant. So it's just this kind of shape like this. And take it around the other side. There's a pretty good ellipse, huh? With a focus here and a focus about here. Now we said last time, actually, planetary orbits are like that. A planet orbits the sun with the sun at one focus in an ellipse and sweeps out equal areas and equal times, all sorts of neat things that Kepler and others found. And so that's another definition, is that, threw it a little wobbly because I left the pin. It actually makes a pretty good ellipse if you do it carefully. Shouldn't rush. What you want is d1 plus d2 equal the given fixed number 2a. And so you say, what does that mean in coordinates? That means if you were to take this and center it at the origin, so the origin is halfway between these foci. There's the x-axis, there's the y-axis. And the arbitrary point xy is up here on the ellipse. Suppose we place this point at minus c0 and this one at plus c0. So we're saying the focal distance is c. Distance from the center to each of the foci. Now, what does that tell me? That tells me that the square root of, like if I do it this way, at any point here, xy now, the distance to this one, d1, is square root some square of these numbers. Let's see, the x distance, you have x plus c, so it's square root x plus c squared, c. X plus c is this distance in the x coordinate, and you make a triangle. X plus c by y. So square root x plus c squared plus y squared plus this distance over here. This one would be x minus c is the x coordinate, and the y coordinate is y. So square root x minus c squared plus y squared. That has to all be equal to 2a. If you solve this, it's a little bit of algebra, so I'll just say you apply algebra. You add that, you subtract one of these over and square both sides and rearrange it, square both sides again. What you wind up with always is an equation of this form: x squared over a squared plus y squared over b squared equals 1. So it always comes out to be that equation if the center is 0, 0, and you put the foci at plus or minus c on the x-axis. So let's draw that one down here. Now, what is b? C was the focal distance. 2a was the length of the string. Turns out that b satisfies this relation. A squared equals b squared plus c squared. So it always comes out to be this equation with this relation between a, b, and c. Now, furthermore, this was for foci at plus and minus c on the x-axis. What about foci on the y-axis and it's centered at 0? Suppose it's 0 plus or minus c. Now, instead of looking like this is the one we had. It was oblong this way. There's minus c0 plus c0. Now we're going to have an ellipse that goes longer this way. 0c, it's not blocking over, if you can't see, move. And 0 minus c. I'm trying to stand out of the way of the camera for the people online. 0 minus c. In this case, you get exactly the same kind of thing. It just changes the equation a little, and it comes out to be x squared over b squared plus y squared over a squared equals 1. Where again, a squared plus b squared equals c squared. That's an ellipse vertically. So you memorize those two equations. They're very important. The two equations, also the a squared plus b squared equals c squared. It looks like the Pythagorean theorem, but a squared by itself instead of c squared, right? Those are the standard equations for ellipses, and then you can figure out how to sketch an ellipse. Because what happens here is, if you think about it, if I put in y equals 0 in this equation, what happens? I get x equals plus or minus a. I get these 2 points here. These are called vertices, a0 and minus a0. If I put x equals 0, then y has to be plus or minus b to satisfy this equation. So it goes up to 0b and 0 minus b. Similarly, on this one, I have plus or minus b on the x-axis. I have b0 minus b0 and 0a, 0 minus a. There are the vertices on this one. So you have foci with on either axis, and these two different equations, where in those I should note always that a always comes out to be bigger than b. In fact, it's also bigger than c, right? Because a squared is the sum of b squared plus c squared, so it has to be bigger than both a and b. Both a and b. All right. So now that tells you how to sketch an ellipse. Suppose I give you this equation. Sketch and find the foci of the equation 4x squared plus 9y squared. I'm probably messing up the picture on that now. Equals 36. How do I know that's an ellipse? How do I know that's an ellipse? I divide through by 36 to get 1 on the side by itself. I'm going to erase this part. Because when I divide by 36, it's equivalently x squared over 9 plus y squared over 4 equals 1. I can write it as x squared over 3 squared plus y squared over 2 squared equals 1. A is 3 and b is 2. I immediately sketch it because it's this standard form. I draw this picture. I draw it out between plus or minus 3 on the x-axis, plus or minus 2 on the y-axis. I draw this oval shape, like you saw with the string. And then the foci, what are the foci if I need them? Well, according to this one, c is the square root of b squared of c, a squared minus b squared. So it's square root of 3 squared minus 2 squared is square root of 5. So the foci are at square root 5, 0, and minus square root 5, 0. There's how you can figure out the ellipse that goes with the equation, right? Any questions on that? A is called the semi-major axis length, and you should write it down, because it's 1/2 of the length of the longest axis here. B is called the semi-minor axis length. It's 1/2 of the short axis. So that's names for A and B, and C is the focal length, or focal distance. Now, what if instead I'm having a problem with this equipment here, so I'm just gonna have a little delay every now and then. This time I'm going to give you something else. I'm going to say find the equation giving foci at 113 to 1 minus 11. So example, foci are at 113 and 1 minus 11 in the plane of an ellipse. Find the equation this time. How about that? The first problem is you don't have the right equation even. Why not? Can anybody see why I don't have the equation yet? The right form? Hmm? Well, I'll put those in, assuming these are XY coordinates. But the problem is that, remember, the center of the ellipse always has to be halfway between the foci and halfway between, and halfway across the semi-major and semi-minor axis, but it's not. It's not halfway between the foci. The center, how do I find the center? It's halfway between the foci. I just average the coordinates. It's at 1 plus 1 over 2. 1 plus 1 over 2. 13 plus minus 11 over 2. So I can average those two coordinates and get the center. The point halfway between. Remember the midpoint formula? This is midpoint formula halfway between these. So this is the point 1, 1. It's not centered at 0, 0. So how am I going to get its equation? Algebra to the rescue, right? Remember how to translate things in algebra? Given any equation, doesn't matter whether it's these conic sections or not, you can translate the graph that is shifted across the plane horizontally by a number x0 and vertically by a number y0. How? Remember how to do this? How do you translate the graph of any equation? Just by replacing x by x minus x0 and y by y minus y0 everywhere in the equation, right? You have to replace it everywhere. But now x has to be x0 units bigger to do the same thing you did before, and y0 units bigger to do the same thing. And then it'll satisfy the equation with making those each that much bigger. So what I need is not the standard equation we wrote before, but this modification of it. I say you memorize the standard equations in here, and then memorize how to translate this, and you can figure it out every time. It's not so many equations to memorize. So what we need, we also have another problem. The foci are vertical, right? Here the x coordinates are the same and the y coordinates are different, so the foci must be vertical. So what I need is x squared over b squared, the smaller number since the foci are vertical, plus y squared over a squared equals 1. It's an equation of that form, right? And I forgot to give part of this too. I didn't give you enough information. Foci don't tell you enough. I think I have the semi-major, semi-minor axis like that. Yeah, semi-minor axis length is 5. So here's the foci. Find the equation if also the semi-minor axis length is 5. So that's half the length of the short axis. All right, but I get the equation of this form, and I write x minus 1 squared instead of x squared and y minus 1 squared. This will translate it 1 unit vertically. This will translate it 1 unit horizontally. Now, if you x has to be 1 unit bigger to square the same number here, y has to be 1 unit bigger to square the same number. The center of the ellipse will now be at 1, 1. It's whatever you subtract is the shift. So there's the form of the equation I want, but I know more than that. What else do I know? But that one, right? Semi-minor axis length is 5. What number is that? Remember, half the semi-minor axis was always B. Half the semi-major axis was A, because you went to A0 and minus A0 and B0 and minus B0 on the standard one. This must be B if it's half the semi-minor length axis. A if it's semi-major. So I can replace B squared with 5 squared. So I know the equation looks like that. What else do I know? I know C, actually. C is half the distance between the foci, right? Now, if the focus is at 113 and the center is at 1, 1, C must be 12, right? It's the distance from the center, 0, 0, to either focus. Let's say not 0, 0, 1, 1. To either focus, let's say 113. All right, you just go 12 units in Y, so it's C equals 12 is the distance from the center to the focus. So I replace, I can't replace A yet. I've got C equals 12, I can find the foci. I've got B equals 5, I can find the semi-minor axis length. How do I get A? Yeah, it's Pythagorean theorem except with A under here. A squared equals B squared plus C squared. Don't worry, the C squared equals A squared plus B squared comes in with the hyperbola. So for the ellipse, it's A squared equals B squared plus C squared. The semi-major axis length is the largest number. So A is the square root of B squared plus C squared, which is 5 squared plus 12 squared. If you work that out, the square root of 169 is 13. So A equals 13. Now I can write it in. Here's the equation of the ellipse now. X minus 1 squared over 5 squared plus y minus 1 squared over 13 squared equals 1. This is the ellipse that has those foci and that semi-minor axis length. That's what a bunch of the problems are. They'll give you enough information you can figure it out. They might give you the foci and the semi-major axis length, or the semi-major and semi-minor axis length, something like that in the center. But there's the equation for this one. Now you might say, well, we should multiply it out and simplify it. Well, actually, these things, when you multiply them out, don't look simpler. It's nice to leave them as squares. And what's more, if you leave them in this form, people can see immediately what A and B are and where the center is, all that kind of nice stuff. So usually we just leave these equations here in this form. X minus A squared, X minus X0 squared over B squared plus Y minus Y0 squared over A squared equals 1. This looks like a B here. Then that's a 13. Sorry. That's how you find that one. All right, so the next one is hyperbolas. I can't draw such a nice picture for those, but they're very fun too, and they're very similar. It's interesting is these optical properties and derivation properties are all highly related for these conic sections. Suppose we change the criterion, and for hyperbolas, we say this. These are all coordinates x, y such that the difference in the distances to 2 points called foci is a constant. Some positive number. And we won't go through the calisthenics on this one. It turns out you write the same equation in there except minus in the middle. And when you go through and solve that one, you'll always come up with this form. So we'll say by algebra from an almost identical equation, just change the plus to a minus, you get for a center at the origin, and the same thing, foci at plus or minus C0 on the x-axis. We'll call that the standard position for it. If you put the center at the origin again, foci plus or minus C, but now you demand the difference in the distances be a constant, you get this kind of a picture. Here's the xy axes. Here's the foci, minus C0, plus C0. It looks kind of like this. It's what we showed on the cone the other day. It's actually the same figure. It's a hyperbola. It has two branches. Oops, I didn't throw the right point though. I'm sorry. It doesn't go through the foci. Drawing it through the wrong point. It goes like this and this. You're all engineers, right? You brought pencil so you can erase that, right? But it turns out actually it approaches two asymptotes. So it's different like that already. It goes out to infinity in both directions, and it approaches two asymptotes. And the equation is just a little different. It changes the minus. You get x squared over some number a squared minus y squared over a number b squared equals 1. But this time you do get the Pythagorean theorem exactly. This time c squared is by itself equals a squared plus b squared. So there's the standard equation for the hyperbola with center at 0, 0 and foci on the x-axis. And now I bet you can see what A is geometrically pretty easily, right? That's my blue pen. I don't know what I did with it. I'm going to lose it. They'll use red. That green is not cutting it, is it? I'll mix the green and red and get brown, right? Take art class. So, anyway, all right, so there's a hyperbola. But the point right here on the x-axis, this actually has to be a0, and this actually has to be minus a0. You see that by plugging in, right? If you put in y equals 0, then to satisfy that x has to be plus or minus a. So those are the vertices for the hyperbola. If they give you vertices, those are those 2 points closest to the center of the hyperbola. What good is b? Where does b come in here? Yeah. Yeah, awesome. It gives you a slope of asymptotes. What you can do is people like to draw this rectangular box of width 2a. So it goes down out to the vertices on each side, plus or minus a. And then they make the height of the box b. So it's the height up and height down is b. So it's a box that's 2a by 2b, a rectangular box. A, B, B, A, B, B. And what happens is the asymptote turns out to go right through the corner of the box. And so the slope of the line must be b over a. Actually, what you can do is you can show it this way. If you solve this equation for y equals 1 plus x squared over a squared, square root, so you get this part of the hyperbola. Then you look at the limit as x goes to infinity, you'll find that asymptotically, and you use your calculus 1 to do this, calculus 2 maybe, you can show that the asymptote is y equals plus or minus b over ax from this equation. And so that means if you draw this box that's 2a by 2b, the asymptote has to go right through the corner so that the slope is b over a, right? The asymptotic behavior of this equation, this x goes to infinity, y equals plus or minus b over ax. This one over here being minus the slope is y equals minus b over ax. And there's your asymptotes. That's how you draw a hyperbola. And then again, if it's not centered at the origin, you have to translate both the equation and the asymptotes. But you memorize this one, and then just, oh, here's the asymptotes. I should write these over here too. Y equals plus or minus b over ax. Memorize all three of these equations for the hyperbola. And then what happens if it goes the other way? Suppose I want the branches to open up and down instead of left and right. Well, all you have to do to turn the graph the other way is interchange x and y, right? Because that's equivalent of flipping the axes, interchanging their directions. So if you just interchange x and y in any equation, then it flips it the other direction like that to be vertical instead of horizontal. So for hyperbola opening up in standard position, up and down, we use this equation instead. We use y squared over b squared minus x squared over a squared equals 1. Well, really, to interchange x and y, I should have left this a and this b like I did with the ellipse, right? This looks just like the ellipse equation, except you just change plus to minus on both cases. But even though that works to interchange x and y, and this is a hyperbola, people like, usually, some looks differ on this actually, people like to leave the b under the y and the hyperbola and the a under the x, because then you have the same asymptotes. Y still approaches plus or minus b over ax instead of a over bx. So most presentations I see, they interchange x and y and a and b in the hyperbola. And the trick is when whatever term is positive, if the y term is positive, it opens up then, but if the x term is positive, it opens right. Right, so this one is a horizontal if the x squared term is positive, and it's vertical if the y squared term is the positive term. So this one will look like this, opens up like this, and down like this. It still has asymptotes, y equals plus or minus b over x, because we didn't change a and b, or because we interchanged a and b as well as x and y. So this is y equals b over ax. This is y equals minus b over ax. And it goes through this time 0a and 0 minus a. And there's an important distinction here too on the ellipse. You notice that a always had to be bigger than b, right? It was the biggest number. And whichever variable you put the a squared under was the one that had the semi-major axis. Not so in the hyperbola. And here a and b can be equal or b can be bigger. So don't require b bigger than a. It's still a hyperbola. Don't require a bigger than b anymore. Here's my blue pen. It appeared again. All right. I must have hid it under the corner of the backpack. Any questions on all that? All right, so let's try a problem with that one then. Suppose the vertices are 4, 2, and 4 minus 4. Again, the vertices are these points here on the hyperbola closest to the center. Maybe you want to write that in there. It's vertex, and this is a focus over here at plus or minus c. All right. And besides that, the focal length is 4. What is the hyperbola equation? And what are the asymptotes? Well, first of all, you notice the x-coordinates are the same, but the y-coordinates are different, so this is a vertical hyperbola. By the way, you can rotate all these things in the plane. That works too, but the equations change. We'll see how to rotate them later. For now, always the focal axis will be vertical or horizontal, right? So how do I do this one? Once again, I can find the center by averaging either the vertices or the foci. The center will be by the midpoint of these, 4 plus 4 over 2, 2 plus minus 4 over 2. It must be at the point 4, let's see, minus 2 over 2 is minus 1. So there's the center of this hyperbola. Now, which equation do I want? Do I want the vertical focal axis or the horizontal focal axis? Well, the x-coordinates same and y are different, so the foci are vertical, right? The y-coordinates different. So vertical foci and vertices. Let's just leave vertices off. Vertical foci. Now, what do we know besides the center? By the way, this is x naught, y naught when I translate it. I'm going to do the same thing. I'm going to take the standard equation. It's the other one that I had to erase. And I'll just replace x by x minus 4 and y by y minus a minus 1. Right? But the vertical foci, I know this. The distance from the center to a vertex is a, right? So a equals the distance from the center, 4 minus 1, to either vertex, let's say to 4, 2. So it's 3 units up. A is 3. I know A. Now I also am given the focal length. What's that? That's always C, right? So C equals 4 and A equals 3. Now what do I write to get B? Puts you to sleep, huh? Pythagorean theorem, right? For the hyperbola, it's just C squared equals A squared plus B squared. I infer that 4 squared equals 3 squared. That's A squared plus B squared. So let's see, 4 squared minus 3 squared is 7. B must be square root of 7. Now don't use this equation because it's vertical. I use the other equation and I translate it, right? Shift it over in the plane. So the equation, since for vertical foci, I have to put the y term first. Y squared over b squared. Well, let's see, b is square root 7. Minus x squared, right? Because it's hyperbole, put minus instead of plus. Otherwise, it's just like the ellipse. That's what's nice about it. It's not so hard to remember like that. Over a squared. Let's see, a was 3 squared equals 1. There's the equation. But instead of putting x and y here, I put what? X minus the center position for x, y minus the center position for y. So the center is at 4 minus y, I put x minus 4, y plus 1. There's the equation for this hyperbola. Right? Kind of fun to plot these with MATLAB or your other favorite program, too. They do a nice job. All right, those are the two hard ones. And I get the asymptotes. What are the asymptotes? I'm supposed to put y equals plus or minus b over ax, right? But it's no longer centered at 0, right? So I have to translate the axes too. It's y minus y0 equals plus or minus b over ax minus x0. That's the equation for the asymptotes. So I've got y minus 4 equals plus or minus. See, b was square root 7. A was 3. x plus 1 here comes out. So there's the asymptotes to go with it. You have to translate the asymptote equations too. Now finally, we also have circles and parabolas. We can do those quicker because you did lots of those in algebra, right? What's the standard equation for a circle? I'm not even sure they have any circle equations in this section, but we will use them later in the rest of the semester. Circles look like what? What's their equation? Yeah, you're doing, for the center, it's just x squared plus y squared equals r squared. For centered elsewhere, it's x minus x0 squared plus y minus y0 squared equals r squared, where r is the radius and x0, y0 is the center, right? If this is just the square of the distance formula, actually, right? It says the distance from x0 and y0 is always equal to r, to xy is always equal to r. It's the distance formula squared. So that's how you write an equation for a circle if you ever see it. How about parabolas? Parabolas, let's do the ones opening right. A parabola has this thing. It's all xy with distance from a given point, 1 point this time, called the focus, again, to a given line not containing the point, called the directrix. Directrix is constant. So it's a similar definition, but only one focus this time. Some constant A. And what you get out of that, and again, if you write the distance formula and square it and solve it, you get for a right opening parabola like this. Suppose you put the directrix, I'm sorry, let's do a vertical one, sorry. Put the directrix down here at y equals minus A, y equals minus C, and up here at 0C. And the idea is every xy up here has to be the same distance from this focus at 0C as it is from the line if you drop a perpendicular. Well, it should look the same distance. I didn't quite get it, but that's the idea. And what happens? It has to go through here because the distance here is equal to the distance here. And let's call this y equals minus A and 0A here. All right. And then the equation always comes out to be y equals, x squared equals 4ay comes out to be the equation that you always get for an upward opening parabola. And it looks like that thing you knew and loved from algebra, right? It's just a nice arch shape that the Romans used to use a lot of in their architecture and so forth. X squared equals 4ay is the standard equation for parabola. I think I'm out of time, so I'm going to have to do a parabola next time. But I think you can do all the homework anyway. It's mostly difficult with the parabolas and the ellipses and hyperbolas. But now you can see this is for a parabola opening up. What if it opens down? All you got to do is put a less than 0 to open down. And then if you interchange the variables, right, y squared equals 4ax, this is a left or right with a positive or negative. Right if a is positive, left if a is negative, parabola. All right, so that is all that we have time for today. Try all those conic section problems. That's probably all I'm going to say on conic sections. We need to try and catch up. But bring a question next time if you want to do one more parabola. I might do one, maybe.